All right. So thanks everyone for joining us today. I hope you all had a great week, great vacation. Today we have the pleasure to host Ankit, who is a research scientist at the Google DeepMind office here in Montreal, and he'll share with us some thoughts on AI for proving and disproving conjectures in mathematics. So before handing the mic to you, Ankit, let me remind you all of some house rules. So as usual, clarification questions will be allowed to be asked during the talk. So today we don't have any mobile microphone. So for people in person, if you have a question, just raise your hand, ask your question, and Ankit will repeat it for people online to hear it. And for people online, you just have to type question or I have a question in the chat. And when the time is right, I'll let you directly ask it. There'll also be some additional time at the end of the talk for people to ask a further question, make some comments, or have a more informal discussion with Ankit. That's pretty much it for me. So whenever you're ready, Ankit, floor is yours.
Thank you, Rim, for organizing it, and thank you all for coming. It's a pleasure to be here. I think I'm coming here for speaking as a T-Talk after 5 years. Immediately after my PhD, I came here to talk about my PhD work, and here I am. I'm sad that I took 5 years to be here. I should have come here much more often, and I hope to do so. But yeah, here I am to talk about some of the work we did at DeepMind Montreal and in collaboration with folks at Google DeepMind London on how we can use AI to make some advances in mathematics. So I would be talking about I would start with probably lowering the hope that I'm not going to prove or disprove a conjecture here or something. But I think we have made some advances how we can use AI for automated theorem proving, as well as improving some new lower bounds for some open problem in mathematics. So we have discovered some new things by using AI, and I'm happy to share it with you. So just to begin, AI and maths in the contemporary world have advanced a lot in the last 3-4 years, and there is a lot of push to use AI to make some great advances on core mathematical and theoretical computer science problems. On the left is one of the work at Google DeepMind London on how AI was used to guide the intuition of the mathematicians. So it was a collaboration with mathematicians where they ended up proposing some new conjectures in knot theory, and then mathematicians went on to prove some of those conjectures. So the AI in this case proposed some new knowledge which could be conjectures, and mathematicians were successfully able to prove it. So it was a great case of how AI can work with mathematicians to discover new knowledge. And on the right side here is matrix games. Probably some of you have heard about the alpha tensor, where AI went on to discover some new matrix multiplication algorithms for different sizes of matrices. So matrix multiplication is one of the core problem, one of the fundamental problem which we used every day, for multiplying matrices whenever we are doing deep learning and all that. So here by this work, AlphaZero was used to discover some new algorithms for matrix multiplication. So it was not like that a particular matrices were multiplied faster. So it explicitly discovered some algorithms for matrix multiplication. So this has been a trend, and AI is getting into making more and more advances in the mathematics. And yeah, just to start with, I would start with a quote from Bertrand Russell, that the fact that mathematics is symbolic logic is one of the greatest discoveries of our time. So a lot of us, AI has made advances in logic, and the initial, the GoFi AI was dealing a lot with the logic. So, and mathematics is one of the, is actually symbolic logic in a lot of situations we encounter. And there has been a lot of interest, even not within DeepMind, even externally as well. Some of you may have heard about the IMO Grand Challenge, which is basically so there is International Maths Olympiad for I think high school, and for high school to discover high school prodigies in mathematics who can participate in this Olympiad. And now the challenge is that can AI win a gold medal in that Maths Olympiad? This was proposed back in I think 2021, but it comes with the caveat that the mathematical problems are formalized firstly by humans, and then AI is operating in that formal world. So in like lean or and so on. And there have been some recent papers of using even language models to make advances in this domain, from Facebook, OpenAI, and so on, from Meta, I should say. Yeah. So in this talk, I'm going to talk about two of our works. Uh, so this is slightly older work. The first work we did with AI for automated theorem proving. So we started with the first order logic, and so we use the idea of hindsight experience replay, which is idea in reinforcement learning, to introduce this to build a first order logic prover, which became the state of art and built many symbolic had written many symbolic provers on some of these theorems. So this was published at ICML 2022 and AI for Theorem Proving Conference at 2022. And recently, so we dealt with, so this is about proving. So in the automated theorem proving, we're dealing with like the formal languages, and yeah, in the first order logic. So we are going on to prove theorems. But then we ask the question, can we use the same AI to disprove some things? Because when you are targeting some open conjectures, you are not sure whether they are proved, whether they are correct or not. Some of the conjectures after a while turn out to be false. So we always want to see whether we can also disprove some of these conjectures. So on this slide, we didn't disprove this famous conjecture by Adosh. I would talk about a very simple conjecture in graph theory by Adosh. And but we improved some lower bounds for a lot of sizes which were not known a priori in this domain by using AlphaZero and taboo search techniques. So this work was recently published at was put forward at NeurIP's Math AI workshop. So to start with automated theorem proving, I would probably give a very short primer on the first order logic as well to explain the domain what we are dealing with. And one thing I want to say is that a lot of these ideas are definitely applicable to like the higher order logic and other things as well. So the logic, if you think it operates at like if I have to do a broad classification, there is propositional logic where you encounter SAT like problems. And so here there are like mathematically you can solve a lot of these problems. Like it is still hard, but the SAT solvers are pretty strong. And so there is that level of logic called propositional logic. Then in the middle there is a first order logic where you can formalize a lot of mathematical knowledge. You have very simple actions. I would describe some of these actions when you operate in this logic. But you have essentially like these quantifiers like for all, and there exist, and you can encode anything like any open mathematical problem in the first order logic. And there are very strong baselines. This is like analogous to what we have in chess, like the stockfish like provers, which people have built over the 20 years with lot of heuristics. So they are pretty strong. And so we started with like, okay, can we improve on those by using machine learning? And then there is higher order logic. There has been a very great interest in higher order logic these days, especially with the lean. And there are many open problems. There are complex actions and a lot of mathematical knowledge you can do in this domain. Like you can have induction and a few like the mathematical constructs which which mathematicians use directly in higher order logic. So we started with first order logic because it was simple. We were coming from a non-logic background ourselves, and we thought like it's an easy place to start with, and we understood that well, to be honest. But at the same time, like some of these ideas are applicable to the higher order logic and should translate there. So the motivation was that the deep learning so far, most of when we entered the first order logic things space, there was application of deep learning, but the most use of the deep learning was limited to basically they would take a prover which has a lot of heuristics and they would add some deep learning knowledge on the top of it. So it's like you take and then you improve things slightly. So the heuristic approaches were still state of the art, and most of the heavy lifting was done by the heuristic based approaches. So if you see one of the open source prover in this case it's called eProver. It contains 100K lines of code in C++, which was just describing the heuristics. So they find new heuristics and they add to this prover, and they keep on doing. And now they have like over the years they have built a very strong prover. As I described, many ML approaches were built on the top of E, and none of them we observed was trying to learn from scratch. So it was like, so one of the aim we wanted was that we don't want to use these heuristics, and we want maybe the machine learning can discover some of these heuristics on its own. So there was some recent work at that point from IRL, IBM Research Labs, which was called Trail. So it uses reinforcement learning, but it also means it was behind eProver on, like, if you compare with the best setting of the eProver. So just to give you like how this this space looks like. So there is a competition organized in the first order logic community. They called it as like the World Cup of first order logic theorem proving. And if you see, there are some provers like Vampire and E, which are winning over the years. So these provers have like crushed these competitions, and none of these provers were coming, like none of the provers were, or machine learning approaches were coming close to these. So this was the space we entered, and we were asking the question how we can use machine learning or deep learning to outperform some of these provers, as we did with the AlphaZero with the chess and so on. So just to describe first order logic, how things look in the first order logic. So we are given a conjecture in this form. It is like there exists a y for all x, where py implies px. Say this is the conjecture. So essentially what we will do, the first step in this pipelines is that you take this conjecture and you negate the conjecture and you put it into something called clausal form. So basically we derive clauses out of it. We get rid of the quantifiers. This is a mechanical step which is pretty standard in all the provers. You need not go into the details of it, but the conjecture essentially looks like that there are two clauses between which there is an and we have converted this conjecture into negated form, negated conjecture. So and then we add this with the, so you see there are a lot of quantifiers. I'm not going into the technical details of the first order logic, but essentially we are deriving some clauses out here. So other examples are here. So yeah, axioms of group theory can be encoded in that form. So you have some hypothesis, and so you are also given apart from conjecture, you're also given some axioms which you assume to prove this conjecture. So then you take all these things and you convert it into something on the right, which is called CNF in TPTP syntax. There is some syntax. So these are all the clauses which have and between them. And now we want to use some of these clauses to basically derive a false. Because as I told you that we have negated the conjecture. So essentially we are doing a proof by contradiction or proof by refutation. So we take the conjecture, we negate it, and we say that the axioms and the negated version of the conjecture leads to a false statement. Something like x is true as well as x is false, which is essentially a false statement. So the operations, why first order logic is like interesting to operate from a research perspective is that there are only two operations to deal on all the clauses. So the first operation is called resolution, which basically takes two clauses and combines them. Like say you have a statement not p of x or q of x, and you have another statement, say p of c, where c is a constant. So now you can combine, if you take an and of these two statements, essentially you would say that q of c, you can derive q of c out of this, that q of c is true. And similarly, we have a factoring where if you have that the two predicates are same, p of x or p of c or q of x, you can derive a new clause out of it, p of c or q of c. So just for simplification, what you can assume that, so we would be given a bunch of these clauses, and we have two actions to operate on these clauses. If the structure is similar to some of these things, we can derive new clauses out of it, and we can add that to like our knowledge base. So the q of c statement is derived here, and you can keep going on and on forever. So if you assume that you have a lot of you are given some initial clauses, at each step of like these operations, you would derive a new clause, and that gets added to your knowledge base. And then you can so you're basically the number of clauses you are operating on, or the number of states or number of these clauses you're operating on with these actions, that is increasing at each step. So, but the interesting thing in first order logic is that only these two operations are sufficient enough to prove any theorem which is provable, theoretically speaking. So if you keep running these operations over and over again and again, you can, if that statement is false, you should be able to reach false. The issue is that you can probably go on a very weird path, and you can keep driving infinite clauses without reaching false. And the space, because the space is increasing, so you can't search the whole space, or you can't exhaust the tree very easily. So I would also describe an algorithm which everybody uses to operate on this in formal terms, and this is used in all the. It's a search algorithm. It's like A star sort of search, but in slightly convoluted way. So this algorithm is there in all the provers. So you are maintaining two queues in this algorithm. Yeah, so one queue and one set. So initially you would put all these queues, all these clauses on the queue on the left, which we call as the unprocessed clauses queue. So you put all your axioms and negated conjecture in that queue, and the set of processed clauses at the top is empty. At each step, and you have somehow a cost function on the unprocessed clause queue. So you have cost associated with each clause. At each step, you take like the clause from it which has the least cost. And so how the cost is coming, I would come to that. So you take the clause with the least cost, and you either add it into the, if there is nothing in the processed queue, you would add into it. But say if there are some things already there in the processed queue, what you would do is that you would pick a clause, in this case CL1, and you would check whether this clause makes any other clauses redundant in the processed queue, or this clause itself is redundant. So the top set you are maintaining are the set of things which you want to operate on. And so basically you are checking, you don't want to add unnecessary things there. So you do some sort of redundancy check with all the clauses in the process queue with this clause. And if you derive, say, you would also apply the actions of resolution and factoring on this clause. And if you derive some new clauses, some new knowledge out of using this clause CL1, you would add back to the unprocessed queue. So assume that if this queue has 5 clauses and you pick a new clause out of it, you can potentially derive more than, like, it's not only you will derive 5, because a resolution and factoring between the two clauses can also happen in multiple ways. So you can derive a lot of new clauses, and you have your unprocessed queue can keep increasing. So that is how it operates. And what now the magic is how you would derive the cost of each clause, how you can define the cost of each clause. So people have derived heuristics for defining the cost of each clause. The simplest heuristic is that you take like the clause which is smaller, because we assume that all the mathematics knowledge, the theorems, the final theorems, and the proofs are smaller. Like if a theorem is interesting, the proofs are smaller, and essentially also you have to reach false. So you have to go to a clause which is basically which is null. So you are biasing the algorithm towards smaller and smaller clauses. So you take the clause which is smaller, and so the cost is determined by the length of the clause. So that is the simplest of the heuristic. But obviously people have derived a lot of new heuristics on the top of it. Yeah, as I said, can be as simple as small clauses, could be very, very smart checks here for redundancy, and so on. So if I have to simplify this algorithm at a higher level, you can also assume that you're given a set of axioms and negated conjecture on the top row, and you are deriving new clauses out of those continuously. And as soon as you derive a false, you would pick that clause, like, say, because it has length 0 and all that, and so you have reached a proof. So you have reached a contradiction. So you basically, the yellow portion here illustrates a proof, and that the remaining portion is like the unnecessary search you had done. So this is how the saturation operates. In this work, yeah, so this, I just described the background of what space we are in. So we want to reach the contradiction as fast as possible. And in this work, we make 3 contributions. So we propose this idea of incremental learning for theorem proving. I would describe that. We also introduce the idea of hindsight experience replay, which is how we adapt the idea of her to theorem proving and how it is super useful. And we also describe, I haven't described because we will use deep learning, how we will describe the clauses. So we have also introduced a new representation, which is transformers with spectral features for logical formulas in this. So I will move forward. So how machine learning is used so far in theorem proving? So far, how people were doing machine learning in theorem proving. So basically, they would do this kind of search with a saturation, and so you get to know the proof path. Now, each clause, you know that whether it was a part of a proof or not. So given any node on the yellow path is a positive example, and any other node which is not on the yellow path becomes a negative example. So given the axioms and the negated conjecture, you basically want to classify a new clause as 1 or 0. So if it is a part of proof, that is 1. If it is not a part of proof, it is 0. So basically, you do this, you learn this classifier, and ultimately you use this classifier for weighting the cost in the saturation algorithm. So the people can think of like that, yeah, why we are not using the RL in this setting. We have reduced the problem to classification. Why people have not used RL? So people have tried a lot to use RL, and we had also tried a lot. But the issue is that we don't have. It may be the case that somebody can make the RL work here, but one of the issues we encounter here is that the action spaces. So you can also think of like all these clauses as the derived clauses as the actions which you will pick instead of assigning them a 1 or 0 clause cost. So, but if you start doing that, your action space is increasing exponentially. So from 2 clauses, you are driving a lot of new clauses. So your action space is continuously expanding, and it becomes challenging for any RL algorithm to handle it. So Trail used it smartly, but still it is lagging behind the heuristic provers. So one thing you can probably see is that theorem proving is a non-stationary task. So you are basically state space is increasing, action space is increasing, and you have to go towards the unknown areas to prove some of these things. So one thing what we proposed is that we change the paradigm from supervised learning to an incremental learning. So far, what people were doing was that they would have a training set and they would have a test set. So the training set, on training set, they would be given a bunch of proofs. They can learn what is a positive example, what is a negative example. They would learn a classifier, and then they would propose a test budget. At the test time, they would have a small budget to test this problem on, whether it can be proved or not. And they were competing on this setting. So instead, what we thought, like, this is very unrealistic. If you are trying to prove something unknown in the mathematics, or like you are trying to push the boundaries, it's like an exam setting that you trained, and then you write a 3-hour exam and you do that. So it is good for some situations, but probably not great for this setting. So we instead take it to what we call as research setting, which is much more realistic. So we assume that we change the setting in the form of that you are given a pool of conjectures. You are not given any proofs, and you continuously learn on these pool of conjectures, and whatever you prove, you learn from that to generate new proofs, and you keep on going. So I just also want to keep a tab on the time. Okay, so what we are doing is that, yeah, you are given up. So in this case, you are not given any proofs at all, and can you learn on the proofs which you generated yourself? So this is the setting we are going to improve on. So you start with the conjectures. Initially, you would not be able to prove anything. Then you proved something. You would learn from it and keep on going on, and so on. So we tried a lot of approaches in this. We also tried, like for the first case, we also tried search plus imitation. It didn't work well. We also tried like synthetic problem generation and so on. So I'm highlighting some of the approaches which we tried, which didn't work well. Some of these papers are also out there on the web. And the setting, when we were doing this, like the research setting or the incremental algorithm setting, is that we had a distributed setup. We give all the problems to a problem manager. Problem manager would sample a problem from the queue. The problem would go to the actors. The actors would apply the saturation algorithm on that with some cost function, with some very crude cost function initially, and which is now, and if it generates if it proves something, it will give an training example. We put it in a replay buffer, and then this cost function is learned as a classifier in this case, and then we send the parameters to the actors. So basically, the actors and the cost function is continuously improving as it is generating more and more proofs. So the model is trained to be classifier, and the objective is whether the clause appears in a proof or not. Yeah, so these are some of the details. Probably I will skip. And so this led to some improvement in the results. But one thing you can also imagine I give you a pool of conjectures where all the conjectures are really hard, and with some initial cost function, you are not able to prove anything at all. What you will do in such a setting, because you don't have any training data. So then we ask the question, can we somehow use our failed attempts in the proof to prove more things as well? Right now, we are just using the attempts where we successfully proved some conjecture, and we are throwing away all the failed examples. So that brought us to the idea of hindsight experience replay. So as I described, if the curriculum is lacking, if we can't prove any conjecture initially, and then incremental learning alone can't work at all, because you don't have any proof data to learn from, and so you would not improve your cost function. So the idea of hindsight experience replay was proposed back in in reinforcement learning in 2018. And the idea was pretty simple. So you want to reach a particular goal, and you would attempt to target that goal. And if you don't reach that goal, wherever you reach, you assume that if that was the goal, so I know what is the path to that. So I would turn that to be the goal for my learning, and basically change my problem for learning. So if I had to reach this new goal where I actually reach, I know the path to that. So I have training data for that. So exactly the same thing what we did with the theorem proving, that we wanted to use our failed attempts. So assume that this was a successful attempt in the proof, and this is a case of failed attempt. So you tried a lot of things for a particular time, and time limit is reached, and you are not able to prove anything. You are not able to prove basically reach false if time runs out. So then what you can do is you can take any of these clauses. So any of these clauses at the bottom and which are below the top row are the clauses which are derived from the previous clauses. And so we can assume that we can make a theorem out of those as well. So in this case, so what we do is that we take this goal where we reach, we basically negate that goal and add that as in our axiom set. And now you have a path to generate a contradiction out of this new theorem. So you're not solving the theorem which was proposed to you, but you're solving another problem which is related to it. And probably because you have training data for that, and now learning on that may help you to go towards your to generate a contradiction, and eventually lead to the learning may lead to proving the original theorem. Because you have this path of reaching the goal. From the negated goal, if you just combine this goal, you are reaching a contradiction. So we have suddenly turned this data sparse regime into a data rich regime, where from all failed attempts, we will sample the goals, different goals. Now, how the goals are sampled, we also apply the same techniques that the goals, because we want to reach a false, ultimate goal is false. So you sample the smaller goals which are there. And we use this idea of, now I haven't so far described how we do how we represent the logical formulas. So I won't go into the detail of this just in the interest of time, but you can imagine that the representing logical formulas, it's now probably it is pretty obvious that we should directly go to the transformers, but there are a lot of invariances in the logical formulas. And you can derive a graph-like structure, undirected, a directed acyclic graph-like structure from any logical formula, which will capture all the invariances, because you can write A or B as B or A and so on. So that is very natural to do. Now the graph representation is good, but probably whosoever has played with the GNNs, they are slow. And then on the other extreme is the idea of using transformers as such, which captures where you are reading the logical formula as a sequence, and you basically can imagine that we are constructing a fully connected graph for this. But the essential graphness which was present in the original logical formula, that was lost. So what we introduce is this idea of spectral features. So we wanted to keep the graphness, but we want to be efficient for the transformers, like how the transformers, like even the architectures and like the computations, everything is super scalable right now. So we wanted to keep both the things. So what we introduced is, instead of positional encoding in the what we use in the traditional transformer, so we take the graph, we compute its spectral features, and we give spectral encoding to this. And from the Laplacian, I can talk more about this if somebody is interested separately. But when we switch the positional encoding with the spectral encoding, we derive what we call spectral transformers. And we also played a bit with the time allocation strategy, how much time we should give to each goal, to each new, the goals which are derived from failed attempts. We use the idea of uniform budget scheduler from another work. Again, I'm skipping this in the interest of time. Just to the core idea is that we should pressurize it to generate shorter proofs. So we give the time initially some small time and exponentially increase the time, but we make, say, like 8 attempts of 1 before making first attempt of 8 seconds, and so on. Yeah, so I will come to the experiments and results of this work so that I have time for talking about the other work as well. So we had some baselines here. A lot of these baselines were derived from eProver. So one is eBest, which is like running E in its best mode and with various time limits. And there was the eBasic, which is basically where we turn off the E's heuristics and how we do. And then there was this work on Trail, which was using RL for theorem proving. So we ran E, just to be fair, because in our case, we had proposed this setting where we take all the theorems and we run it together on these theorems, where we sample different theorems at different times, to be fair. And we ran this prover for 7 days or 5 days together, like on all the theorems. To be fair with the E, we ran E also from all the time limits from 100 seconds to 7 days. And on each theorem, we gave it a chance, we gave it a fair try that if E can run and do its search for 5 days or 7 days, how many theorems E can prove parallelly on so E is running in a parallel thread on each theorem separately for 7 days. And the results look like this. So there are these 2 data sets. One is MTPTP 2078, which is a slightly harder data set. And both of these data sets are derived from Mizar 40, which has some 60,000 theorems in it, formalized theorems. And the first is for the research purpose, these data sets were created of 2,000 theorems. The M2K is a much more easier version, as you can see. So on the easier version, because E is tuned to perform well on M2K, we are slightly behind E, but not so far. There is on the E best setting, we are slightly behind E. But on MPTP 2078, which is a much more harder version and a more representative of the below data set, we outperform E, and we outperform Trail by a great margin. So how our prover scale with this, with the different times over the 7 days, we prove more and more theorems. So this is how it looks like. On the x-axis is the running time, and the number of theorems proven is on the y-axis. And this is also another interesting proofs that our proofs are shorter than E 99% of the times. So we are plotting on the y-axis our proof length, on the x-axis is E's proof length, and as you can see, most of the things lie below y is equal to x line. We also analyzed how many unique theorems were solved by each prover, what was proven by E, but not by us, and vice versa. And you can see, so there were some unique theorems which were not proven by E, but by our prover. So if we combine these two on the top, so the numbers would increase much more further. And yeah, this is also showing the efficacy of having using the spectral transformers. That we tried GNNs, we tried sequential transformers, MLPs, but the spectral transformers performed pretty well on this task. So yeah, so I think yeah, I'm at a good time to shift gears to the disproving side. But happy to hear any questions or small comments if anyone has on this work so far. Okay. So coming on AI for constructing counterexamples. So counterexamples, if you see like in mathematics and graph theory, so I'm taking this example from graph theory, it happens a lot that somebody proposes a conjecture and people, if it's proposed by a big short name, then people assume that that conjecture is true, and people end on doing even writing PhD thesis on the top of that conjecture and proving that assuming this conjecture is true, we will this is true, that is true, and so on. And sometimes it takes a lot of time to disprove a conjecture. For example, this is a famous Tate's conjecture in 1884. Every three connected planar cubic graph has a Hamiltonian cycle, and it was disproved after, I don't know, yeah, 60 years by William Tate by constructing a graph with 25 faces, 69 edges, and 46 vertices. So it was like it took a lot of 60 years to disprove a conjecture. So disproving a conjecture in mathematics is also equally important as probably proving, because it also derives like new knowledge. And by disproving, I felt initially that this problem is slightly easier than proving, because you have to just construct the object which will disobey like the conjecture. So you have to just search this graph which will be good. But obviously the space of the graphs, if you are even talking about the size 50, the space of the graphs is super huge. It's like 2 raised to power 1200 space of like if the undirected matrices, adjacency matrices you are searching for. And this is another example of like the using of computers in also mathematics is also not new. So this is, I think, the shortest paper in mathematics. So on the Euler's conjecture, like so you can read the conjecture, but yeah, it is just I want to highlight, yeah. So people have been using mathematics, computers at least, to disprove the conjectures in mathematics. So we started this project with like, let's pick a probably false conjecture, because yeah, if you pick a conjecture, open conjecture, and it turns out to be true, then you can't find a counterexample to it. So we collaborated with a bunch of mathematicians. And we picked some conjectures which mathematicians themselves think they are false, but they haven't found a counterexample for those. And the goal was that can we generate a counterexample for it using AI and machine learning and disprove that conjecture. And like some of them, our collaborators were really interested and excited by it. Probably like what they can't see, maybe our AI methods can search for, and AI methods can guide us towards those. So we come to an extremal graph theory question by Adosh. This is a picture of Adosh. The conjecture is like the problem is really simple. So you fix some graph H. If you have a graph G that has n nodes, but no subgraph H, so you want to avoid subgraph H for a given graph with n nodes, what is the question we are asking is what is the maximum number of edges you can have? For example, if say H is just a triangle, so you want to construct a graph of n nodes which doesn't have a triangle, how many maximum number of edges you can have? Or can you generate a construction which will give you the maximum number of edges? So pretty simple, that you want to increase the density of the edges in the graph for a given n number of nodes, and you want to like not have a particular graph, in this case a triangle. So for triangle, it's well known. It's called Turan's theorem. And yeah, so basically it's a completely balanced bipartite graph. You put n by 2 nodes at the top, n by 2 nodes at the bottom, you connect all the edges. That will give you the best construction. Now, if you add like to this edge set that you don't want to have triangle, and also you don't want to have a 4 cycle. So you want to avoid 2 subgraphs, never have a triangle and never have a 4 cycle. Now it turns out that this problem is open. That how many maximum number of edges you can have when you, for a given n node graph, when you want to avoid these things. So Erdős in 1975 conjectured that as n approaches infinity, so for a sufficiently large n, this number should approach n root n by 2 root. I don't know how Erdős came up with this thing, whether how this thing is probably like it is coming from some other mathematical knowledge. And for n is equal to 50, so for some of the n's, there are many edges which achieve, there are many graphs which achieve the optima. So there are many different graphs. You can put the edges in different configurations, which achieve the optima. For n is equal to 50, there is a single graph which achieves the optima of 175 edges, and this is shown on the right. But this is the famous Hamilton. What is the name of this graph? It's a famous graph which has also occurred in multiple other situations. So it's not totally random, but people still don't understand what is going on in this graph. Is there a question?
I'll ask the person to ask it directly.
And I guess it is for, is this for this problem or is it related to the previous part of the? Okay, I will continue and then we can revisit it then. So for n greater than 52, so for n is till n is equal to 52, people know the optimal number of edges you can have. So we have all the data, which graphs achieve optimal, what is the maximum, what is the optimal number of edges, and but people have not been able to find what is the pattern going on. And it looks like the mathematicians believe that God is not playing totally dice here, like that there has to be some construction which is operating in this space. For greater than 52, like to 211, people know the lower bounds and upper bounds, that they have found this thing, and they have also proved somehow that it can't have more than these many number of edges. So it is from 52 to 211. So we started with, okay, disproving the conjecture, which would mean that we generate a construction where like we can prove with the help of mathematicians that for any n, as n approaches infinity, we can generate a graph which has n root n, more than n root n by 2 root 2 edges. And that would be definitely a big result for the mathematics community. But since we picked this problem because it has this nice short-term goal that, yeah, we can also improve the lower bounds for n greater than 52. And we can, like, because the lower bounds are known, they are published, so we can also improve the lower bounds and go on and so on for n greater than 52. How to cast this as a problem on like the agent side, and yeah, as we start thinking about the RL and the agents and generating graphs and so on. So yeah, you have an agent which will generate a graph, maybe with or without constraints. In this case, without 3 or 4 cycles. You have a score function which is coming from mathematicians and like from the mathematical conjecture. In this case, we adopted this simple score function of the number of edges minus number of triangles minus number of 4 cycles. So because for each triangle, you can just remove one edge to avoid that triangle. So it makes sense to have this thing without a constraint. So for like we can always generate a graph with fewer edges, which is without triangles in this case. So the setup is pretty simple, that our machine learning agent or system should give us a graph. We'll score this graph and we'll give feedback to the agent based on that, and probably the agent can improve on this thing. But it's also interesting that we need not graph, because we are talking about the graphs of sizes definitely greater than 50. And it may be harder for the agent to generate this complete graph of like 170 edges and so on instantly. So we can also generate the graph in a sequential decision-making process, sort of like in a like by adding nodes, by adding edges and so on. So like there are multiple choices. The whole problem is in our control, whatever we want to do, how we want to model. So there's one simple choice of that you can cast this problem as that you would add one node. You want to do it sequential decision-making, you add one node at a time. So you start with a 2-node graph with one edge, you add one more node, you add the second node, and you add the third node, and so on. You keep on going. So this would be if I have to talk about like in the RL space, so you are adding nodes at a time. The action space is the vector of actions to all previously connected nodes. And the horizon is like, say if you're targeting a size n, so horizon is like the order n. There is another choice you can think about as a edge adding environment. It's a trade-off between what is the action space versus like the horizon. You can assume that you are not adding nodes at the time, but you can add a fixed edge at a time. Assume that you are filling, because each graph can be presented as an adjacency matrix, you are filling the lower half of the adjacency matrix. So at the first step, for the third node, there is a fixed edge we have decided. The action is only 0 or 1, which is measuring which capturing whether we add that action or not. In the third step, say you didn't add that action, the action is 0, but you are considering this third edge and so on, and you are adding the next edge subsequently. So in each action is only 0 or 1, whether you want to add an edge or not, but you have made indices over all the edges. So now, yeah, and here the number of steps to generate any graph would be, you have to consider all the edges one by one and make this 0, 1 choice. So the number of steps would be n into n minus 1 by 2. So there's a trade-off between like what is each action versus that. And then there is a edge flipping environment, where basically you can flip a given edge in any a graph head. So you start from some graph, and the action space is NC2. So all the possible edges in the graph from 1 to NC2, you would pick a edge and you flip it. If the edge is there, you delete it. If the edge is not there, you don't delete it. It has some advantages. Now you have a hyperparameter, how many steps you should take. But the advantage is from the previous two environments is that you can backtrack. If you made a mistake in this, like say on the third node here, you can't recover back in the whole episode. You don't get a second chance to correct a particular edge. But in this case, you get a second chance. So it provides flexibility to correct mistakes. The other advantage is that in the previous two environments, we were assuming that we were starting from a fixed graph, initial, either an empty graph or a complete graph. So here you can start with any graph, because you can flip any edge from any graph, you can generate any other graph. So it's more like a MCMC setting, sort of what you can imagine. And it also works. We also talked to a couple of other people who are working in this thing. They in chip design and all, and they also found that this environment or this setting, this problem casting works much better. For score function, for the reward, now since we are casting it as a RL problem, for the reward, there was a choice that don't give any reward in the intermediate steps, give a final reward as the number of edges minus number of triangles, 4 cycles. So we observed that is too sparse, and then we move to the reward at each step. So you change a graph, the score of the new graph which you generated, how many edges it has or how many triangles you introduced, minus the score of the previous graph. So we made it a dense reward setting, and if you telescopically add everything, so it will essentially still return, the return would be still the score of the final graph minus the score of the initial graph. If the initial graph is empty, then you are just taking the score of final graph. So we were pretty convinced that we should run some search algorithm with this. Like we tried initially some experiments with the classic RL algorithms, DQN, PPO, but we were like that we need some sort of search component in it. So we went to AlphaZero, which is basically you run Monte Carlo tree search guided by policy and value network, and we try all the 3 environments in this case. And probably you need to know the details of AlphaZero. The policy and the value network is learned to mimic the policies of the search tree and the returns observed by the search tree in the episode. So we are training those networks. The representation, again, I'm not going into the detail here, but the representation was important. We tried a few representations to represent the adjacency matrix of the graph, and we came up with this pair former representation. It is adapted from the Evo former representation of AlphaFold. So here we take the edge features, and then on the edge features, we are taking row-wise attention and the column-wise attention. So basically all the edges are, you can imagine that we are putting the nodes in the grid. So the edges which are connected to that node, we are having a separate attention on the row and the column. So, and then we are passing it through a resonate policy head and value head. So it's slightly complicated representation we came up with. And we tried all this and it didn't work that well. So it was able to generate graphs with the smaller sizes, but for the larger graphs, we were very much behind the state of art. Then we observed what must be happening, what we can do more. Now this is, and then we came up with this idea of incremental learning, or again we came to the incremental learning, but it's more like a curriculum sort of. So we observed what are the graphs look like, what we have generated on the smaller sizes. And a lot of time we observed the graph at size n minus k is very close subset of the graph at size n. So it's not exactly a subset. You may need to delete some edges or add some more edges on the top of it. But it is like the graph at size n minus k is very close to the graph at size n. So it makes sense not to generate the graph of size n like from scratch, but as soon as if we have found a solution for size n minus k, we will use that to guide the solution towards graph of size n. And we also thought, like, since we are going towards the general construction, and maybe like the construction is very much related what is happening in this different sizes together, we need not look at the problem in isolation for different sizes. So we had a setup like this. So we put all the graphs of different sizes in this buffer, and we were storing this. In each episode of Alpha Zero, we sample a graph of size n minus k, where we wanted to aim to find a graph for size n. We sample a graph of size n minus k. And since we are using the edge flipping environment, we can start from any graph. And we give it 50 steps, and we ask it to generate us a graph of size n. Means that like it should be a connected graph of size n. And then once we find that, we put that back in the loop. So now you can imagine that as if we improve the size 50, we will also improve, because the next time when we are targeting 52, we will use the size 50. We will start from 50, and that can guide it much more from 50 to 52 and so on. And we will improve all these graphs together, and the same network is going to guide us. So this is a simple idea based on like the structure of the problem, that the smaller size problems are very related to larger size. So we keep on doing this together on all the different graph sizes by Alpha Zero. And as I mentioned, the edge flipping environment can work starting from any graph. And it also had, because we are targeting, the k was very small. In this case, we targeted, I think, till from 4 to 10. So it's like, yeah, you are adding only 10 nodes. You are not building a graph of size 60 directly. So the episodes were relatively shorter. So this is what we observed. So the Alpha Zero, so I am plotting on the x-axis the number of nodes. The y-axis is slightly, it's a normalized score sort of. So it's number of edges by n root n. So I have divided by n root n just to like normalize it according to Erdos. So if you have to disprove the Erdos conjecture, you want to find a graph which always keeps going up. But like right now, for different sizes are, as you can see, like we are coming closer and closer to this line of 0.36. I think it's the 0.36 line. If we can generate a construction which stays all the time up, we have disproved the Erdos conjecture. But in this case, we are coming down. But we still improve a lot on the state of art, especially on sizes from size 63 to, I think, 139 or so. This is plotted till 100, but we improve a lot on the state of art. Okay, so this is like, okay, we are super happy. Okay, machine learning has found great things by improving the lower bounds of these. We can release these graphs and so on. But then we ask the question, the state of art is on these methods is local search, which is taboo search like algorithm that you search, you flip some edges around you keep a track of what you have flipped in the past, and you keep searching. Very fast local search, no machine learning. So people till now were using the taboo search to generate the graph from scratch. But then we ask the question, taboo search can also work with the size n minus k. And this idea of incremental learning, or like the curriculum sort of starting from a smaller graphs of this size, could also work for like the taboo search. And we did that. And what it turns out, like the taboo search also improves that much on the top of it. So it's a bit like, I will say that it's not very clear win for machine learning, but it's telling us an important lesson, that how to be very sure of the baselines. that you go to your baselines, and lot of chances, if we don't do that, we can say that like, okay, we have improved, alpha 0 has improved on the local search, but we went back and we added this thing, this curriculum idea to the taboo search, and it also improved. And the like I think, and on two sizes, taboo search non-deterministically, on like some runs, it was able to find a graph which was better than alpha 0 by 1 edge. So the full complete picture looks like this. The lower bounds by Adosh is at the bottom line. At the top is what you can achieve theoretically maximum. So we want to find a line which is staying up. So we improved on over the dotted line of the state of art. But yeah, as the size increases, we are still going down. So yeah, I think I am close to finishing. Yeah, one thing I want to highlight is we are analyzing it, and I think a lot of people here must be interested in this, because a lot of people work on drug discovery, G-flow nets, and so on, that this is not a traditional RL problem. In this case, we want to find a graph only once. We know we don't want to find a policy which can be repeated again and again, and we are fine if we don't have a policy. If we find a graph, that is an evidence of that, okay, we have made progress in the problem. We need not maximize, although like in alpha 0. So I'm saying like the shortcomings side, that we are maximizing the expected return, but we need not maximize the expected return in this case. We just care about the final reward of the state. And we only care about the final graph state, even if many trajectories are capturing the same graph. So that is okay. And in a lot of these problems, if you observe, you can assume that like a lot of times there is action invariances and so on in these problems, which are not there in the RL problem. Although so whenever you are casting these problems as RL, so I'm like, the RL is probably the traditional way of RL is not the right formulation. We have to modify it, and probably this also, like this you have observed in like the G-flow nets, drug discovery, chip design, software verification, all these problems, because in most of these problems you are finding a graph. You are interested in essentially a graph which has certain properties and not properties. We are in the maths where the properties are like encoded as these quantities, while in drug discovery and all, it may be harder. Yeah, so we introduced a challenging new learning to search benchmark inspired by an open problem in maths. We improved some lower bounds. There was a essential lesson that curriculum was key to making progress on this problem, and the same things, the next time you try machine learning, the same things could be applied to local search as well. So we should also try to do that. And local search algorithms are very, very challenging baselines for some of these problems. So we should make sure that we should run those. Yeah, I just want to highlight on the last slide that some of my other areas of interest, I have worked in like in the past with some folks from Mila, Bogdan. We worked in like the hard exploration games like NetHack, using demonstrations in reinforcement learning. This is a recent, on the right is a recent work I worked with an intern at Google on like how we can use a small language model and a large language model together to find a cost performance Pareto optimal thing. So you don't want to redirect all the queries to small models versus large models. And so these sort of things I'm also interested in. And lastly, probably you have heard about fun search, which is searching in the function space. So if we want to generate objects like graphs and so on, you can imagine that we can generate the code for those graphs. So fun search paper has come out, which is also generating a discrete object, but they're generating the code for that object. So we are also looking forward to this direction. Thank you so much for your attention. And we can go back to the question. We have to go to the question. Are there, so we can go to the in-call questions.
Can we ask questions? Or?
Yeah.
Okay. You talked about extreme theory. In one of the papers you cite, you talked about amnestic with algebraic combinatorics. Are you aware of a similar article enumerative combinatorics that they use machine learning.
Sorry, you're talking about the constructions in combinatorics, that paper? We are not able to hear you very well. Sorry.
Can you hear me better now?
Yeah, slightly better. Yeah.
Uh, are you aware of similar papers that relates machine learning and other type of combinatorics, like enumerative combinatorics?
So there was one work, construction in combinatorics uh, with neural networks or something. It is from Adam Zassold Wagner, where they use a cross entropy method to again find things in the graph. And Adam is one of our collaborators and a co-author on the second work. And we had compared with that method. It was using a cross entropy method, but it works on a very, very smaller sizes only. And we have the comparison with that method in this work. But yeah, I think this is a upcoming field where a lot of mathematicians also wants this sort of thing, and like to try out different constructions. And if you have any ideas of the problems we should target or any method, we would be happy to collaborate as well. Yeah, but that is the only work I'm aware of from Adam Zassold Wagner, who is a collaborator and co-author in this work.
Thanks.
Galip,
Hi, Anand. Do you hear me?
hello.
Yes. Do you hear me?
Kelly, you can ask a question.
Yeah.
Or I should repeat if you have a mic problem, or like, yeah, you can try probably asking the question.
Yeah, no, I think it's
Okay, so probably I will repeat the question and I will try to see, and probably you can correct me if I'm not interpreting it correctly. So is this software package available for proving or disproving a math theorem? For example, Stokes' theorem for n-dimensional balls is known or proved, but Stokes' theorem for polydomains, there is no proof. There is a suspected form of the formula based on a differential forms, but not proven. It would be a really great result if it can be proven by your algorithm before a mathematician can do it. So I presume it is regarding the first part of the talk, right? Okay, yeah. So the first part of the talk is like assuming, as I mentioned, it is in the first order logic. So the first part would be that we need to encode the theorem in the first order logic. And I think if the encoding and like the assumptions are there, we can definitely try it. And as you are saying that for some small dimensions, it's proven. For n-dimensional balls is known or proved, so it can be useful. But also it's also interesting right now, since that work, there has been a lot of progress on higher order logic. So where you can have like the inductions, and so I don't know whether this theorem exists in like lean or something. So there is a lot of recent work on using lean and these things to prove this with machine learning, to prove new theorems. But so far, I think no one has proven any theorem based on even lean. So it's interesting that I think I won't be surprised. I would like to think like in the next 5 years we will have many theorems which would be proven by a machine learning guided system. But yeah, the first part would be how easy. Sometimes like encoding the theorem in a formal language is super hard. So that becomes the tricky part. And probably, but mathematicians are also leaning towards formalizing some of these theorems. So once we have encoding, like we have encoded the theorem, then definitely this could be tried, and we can see, and okay, we can give it a proof of like for the n-dimensional balls as well. But yeah, I think that the encoding part is also challenging and time consuming a lot of times. So a lot of people are right now targeting this Olympiad like problems, where like for which the solutions are known. It's more like the high school Olympiad. So there also they didn't have great success with the with the just like using the current systems and the language models they are using. So I'll say like it may not be immediately doable, but I think it is. We will have some results in the next 5 years. I don't know for this theorem. I don't know about the complexity of this theorem. Does it answer your question? Okay.
All right, so I'll actually end the talk, but if people have further questions, please feel free to ask it directly to Ankit, and also feel free to reach out directly to him.
Yeah, feel free to reach out to me directly if you have ideas and if you would like to collaborate and so on. So Doina is already here. Doina is also a collaborator on this work, and so yeah, so it would not be a difficult collaboration. So we'd be happy to collaborate and discuss more ideas around some of these things if you're interested. Thank you.
Let's thank Ankit again.